Perfect. I think we can get things started. Good morning, those of you joining us from the west side, and good afternoon for friends from the east. Welcome to CUIIC webinar. My name is Ali Bayat. I'm a faculty member at the University of Alberta, and I'll be moderating today's session, Supersize, that large-scale buried pipe testing at Queen's University. This is the last webinars of our fall CUIIC webinar series. Just a bit of introduction about CUIIC webinars. I think they are presented by Canadian Underground Infrastructure Innovation Center. I would like to thank our education committee. There are about 20 individuals there, chaired by Dr. Jason Luke and Caroline Amit. They have been working hard to put the webinars together. And there'll be a series of webinars for 2023 that's going to be announced. So stay tuned, check our emails and websites, and the information for next year webinars will be there. CUIIC is started basically as a cross-Canada hub for research and education in underground infrastructure. It's located at the University of Alberta, but all our partner organizations are from across the country. A thank you to all our member organizations. We have reached about 45 basically companies so far that are supporting CUIIC's education and research activities. And for those of you who are interested, I would just welcome you and ask you to join. There are a lot of activities happening on education as well as on the research side. So I'll make the introduction short and move to our speaker. We're glad to have Dr. Ian Moore from Queen's University. Dr.
Thanks.
Moore has been Canada Research Chair in Infrastructure Engineering at Queen's University since 2001. There's more than 300 publications examining conventional and trenchless construction of new and deteriorated water, sewer, and energy pipelines, and have underpinned dozens of contributions to North American and other international codes of buried pipe design practices. Recognition of Dr. Moore's work include Best Paper Awards from ASCE, CGS, CSCE, ASCE, NASTT, and medals and other awards from various learned societies and associations. Dr. Moore was editor of the Canadian editor-in-chief of the Canadian Geotechnical Journal from 2006 to 2017, and is currently serving a 2-year term as president of Canadian Geotechnical Society. He's an elected fellow of the Royal Society of Canada, Academy of Science, the Canadian Academy of Engineering, and other learned societies. Please join me and welcome Dr. Moore. And again, I'll stop sharing, and perhaps we can share your presentation.
Okay, thanks so much for that introduction, Ali. And thank you for the invitation to speak to your into this educational forum this afternoon or this morning. And thank you all for zooming in and being part of this. My goal is to talk a little bit about the test facilities we have at Queen's. And so over the next 30 minutes, I'll be introducing you to those facilities and illustrating what we can do with them, some of what we're learning. So it's a sort of an overview of the testing capabilities. And one of the things I'll be doing is reflecting on why we do large-scale pipe experiments. And I thought I'd start by talking about the alternatives to that. One of them is just to test the pipe alone, and that's been the dominant way that we've evaluated pipes in buried conditions, is just test the pipe alone. Here we can see a concrete pipe being tested under parallel plate loading or three-edge bearing to get the deload capacity. And this, for example, with a concrete pipe produces bending moments that tell us about the moment that produces the limiting crack width and so on. But of course, the loading conditions aren't at all like those that are when the pipe's buried. So it completely neglects the soil pipe interaction. And I'm having trouble controlling there we go. So another alternative is to do field testing, and that can be very useful because, of course, we have access to the complete system that's being studied. We're able to do loading under vehicles and so on. There are certain things that we can get in the field that we can't get in other ways, but it can only be for very specific conditions, quite complex site conditions. Often we don't actually know what the site conditions are because we haven't controlled the soil placement, and the soil part of the system is very important. But most importantly, we can't normally load buried structures up to their strength limits in the field because of course, we're normally testing structures that are in service, and nobody likes us breaking their stuff. Another approach is to do small-scale experiments. For example, I've had some projects using the centrifuge at CUIIC in St. John's, Newfoundland, and centrifuge tests can be performed much faster, and they're very good at modelling nonlinear soil behaviour, but you can't really capture the nonlinear behaviour of the pipe. And so that's a tool that I do use, but I don't use it that often because a lot of the problems that we're dealing with is the pipe strength, joint leakage, and things like that, which you can't model in a centrifuge. And so the alternative then is to do prototype scale tests, or what I'm calling large scale tests in this presentation, so that we've got both the pipe and the soil. And because we're doing it in the laboratory, we're controlling the backfill placement. We're getting good understanding of the actual system that we're testing because we're placing the soil ourselves, using normal construction methods, but controlling that and monitoring the way we choose. And because it's in the laboratory, we've got access to equipment like actuators and so on, and we can test up to strength limits. So, as I mentioned, the idea of this presentation is to introduce the large-scale facilities at CUIIC. I'm going to illustrate the research by touching briefly on a project on pipe joints, a project looking at erosion into leaking pipes that are like corroded corrugated steel pipes that are leaking, and so ingress of groundwater produces soil erosion. And we'll also look at the effects of differential ground settlement on joint leakage. Once I think I'm going to be showing you how we can integrate that type of experiment with development of methods of analysis and design methods. And I'm going to finish up the talk by summarizing some of the pros and the cons of large-scale testing. So this shot here shows an overview of the test facility at CUIIC, the geoengineering lab, which is primarily a buried pipe testing laboratory. This is showing the western part of the laboratory, which is primarily composed of a pit, 16 meters long, 8 meters wide, 3 meters deep. At one end, we've got a door, which means we can bring in vehicles and load the infrastructure that's buried there under, say, a tandem axle dump truck or something like that. I think I've got a photograph showing that in a moment. The other half of the pit is specially set up to do trenchless construction. And the particular setup here was a static pipe bursting experiment that was done by one of my former students, John Lever. So the facility allows us to test culverts up to spans of about 10 meters. We couldn't do much more than that. And here's a former student, Andrea, and the corrugated steel culvert that she tested. But we also have the pit, as you saw in a previous photograph, divided into two with a removable retaining wall because it's quite expensive to do very big experiments. So normally we're doing tests in the 8 meter by 8 meter plan configuration. This particular slide shows how we can test under the dump truck, as I mentioned, and a typical unfactored tandem axle load, full service load, would be about 24 tons. But we also have a reaction frame over the test pit, this blue frame, and we can hang our 200-ton actuator into that and apply forces of up to 200 tons onto a set of beams which represent the axles of the truck. So we can test, say, a wheel pair, like one of the steel plates at the end of those beams, a single axle or a tandem axle. And when you make those two different tests and you compare them, the difference is about 2 or 3% in the measured behavior. So that the axle beams do a pretty good job of representing the truck. The configuration for trenchless construction that I'm showing here is made possible because we have a reaction pit on the eastern end of the large pit. That reaction pit is designed to have a 200-ton reaction capacity, either pushing or pulling, if we want to do those sorts of trenchless experiments. We also use that reaction pit for experiments. So we've done hundreds of experiments in the lab since it was commissioned in 2006, but probably scores of experiments actually in this small pit, reaction pit. It's 4 meters by 2 meters by 2 meters. For example, a really nice project looking at hydrofracture during directional drilling, loss of mud from a borehole up to the ground surface through the sand. We also have 2 other facilities. One of them, the first of those 2, is the split box, what I call the split box. It's essentially a normal fault simulator. The box is just under 8 meters long. Half of the box, the floor is supported by these 4 screw jacks, which are sort of represented in that illustration there. And the other half is compacted fill, which sits on the floor of the pit. And the idea is we bury pipes in that zone that's 1.8 meters by 1.8 meters in depth and width. And then we subject that to a normal fault by lowering those screw jacks. And I'll be illustrating my talk briefly with discussions about one of those specific tests. And finally, I wanted to introduce you to the deep burial simulator. This is the newest of the facilities. It's a pit that is 4.6 meters deep, 3 meters wide, and 5 meters long. And it's specifically for 2 purposes. One is to simulate burial up to about 18 meters of cover. And we simulate that by using these 2 250-ton actuators, each of them bearing onto a stiff steel grillage to apply an equivalent overburden pressure. But this pit is also sealed, so it's a bit like a bathtub, and we can do saturated ground testing. And I'll be talking in a couple of minutes about some erosion experiments that we've performed. So the first of them, I wanted to talk a little bit about the surface loading facility at the west end of the laboratory. This is a project that was performed by a former doctoral student, David Besserell. And David was looking at the behavior of joints in culverts. It's a project for the US highway departments about a decade ago. And it involved us testing concrete, corrugated steel, and polyethylene pipes with different sorts of joints under surface loads, understanding the impact of those truck loads on the demands on the joint, the rotations and the shears. And to illustrate this sort of data, I've just got some example here of data we collected from the concrete pipe test. Let me see if I can get the laser working. I can't see that, but anyway, maybe can you see the pointer, Ali?
Yes, I can see the pointer.
Oh, that's great, mate. All right, so here we've got some data where the load was on the ground surface directly over the joint, that one in the middle, that solid line. And the data, this is vertical displacement here along the pipeline, as sort of illustrated with the pipe joints up the top here. And you can see that the impact of that is to cause a sort of rotation, where once the pipe on the left rotates clockwise, and the pipe on the right rotates anti-clockwise, and we get a rotational response at the joint, plus a little bit of shear, bit of shear displacement across the gasket. If we place the load to the left, this is this short dotted line, we get this response of the open triangles with the left-hand pipe again rotating, but then this large shear displacement across the gasket and the other pipe rotating as well. And then, of course, if we put the load to the right, we'll get some sort of shear response that's a mirror image of that. And what this allowed us to do is to establish the kinematics, obtain experimental data, and develop some design models that were proposed for incorporation into, and I don't know why it's not moving forward. There we go. And so for the case of the concrete pipes, we developed some design solutions based on beam on spring models. So understanding that each of the concrete pipes is like a rigid beam that's moving vertically, but also rotating. And then depending on whether we've got surface loading that's sort of over the joint, this is this middle picture here, we'll get that sort of rotation. And here's an equation that predicts that rotation as a design exercise as a function of the different parameters. If we have surface load to the left of the joint, we'll end up with shear. We can get this equation over here, which tells us how much shear we get for that surface load. But also, if you consider the impact of having earth loads produce no joint response if the soil support is uniform. But if, for example, we've got softer soil under one pipe and stiffer soil under the other, then that difference in soil stiffness will also produce shear and rotation. And so a set of design equations for consideration by ASCE for inclusion in the LRFD bridge design specifications. Some of the other experiments we've done in the West Pit, that large span culvert test that I mentioned earlier, we've tested various liner systems, such as the sprayed cementitious liners, a project I did with Ian Doherty for the 407. We've looked at testing direct and indirect design of reinforced concrete pipes, the strength of corroded pipes, concrete like paved inverts in pipes, a whole range of other different sorts of loading conditions and repair conditions. The second project I wanted to just touch on is this project in the deep burial pit, where we've looked at soil water ingress through corrosion perforations. So this little picture here shows a typical situation that you'd see here in Eastern Ontario, where near the waterline of a metal culvert, we'll have wall loss, and that wall loss leads to ingress of groundwater. This is a photograph here on the right, which I took a few years ago. I was actually able to see the erosion void by looking down the spring line of the structure. It's about the best photo I've been able to take of a stable erosion void in this sort of circumstance. And then down here, you can see that this can lead to collapse of the overlying pavement. This was a car that collapsed into a highway in Ottawa about 7 years ago. The guy fortunately was not killed. The passers-by were able to sort of rescue him from the hole. I think he was not entirely pleased about his experience, but he wasn't injured. And we've also done experiments in the past where we've looked, okay, let's simulate a void using an airbag. But I wanted to show you some much more recent work using the deep burial simulator of a project by Oliver Cairns with my colleague Neil Holt, where we're looking at actual erosion into a leaking corrugated steel pipe. And this slide shows the layout of the experiment. Here's an elevation view with the pipe, the ground surface up here, and we'll be raising the water level in the pit up to the crown of the pipe. And that raising of the water level leads to ingress of groundwater through the perforations that were produced. I'll show you a picture of those in a moment, sort of idealized perforations produced along the haunches. This picture here shows a plan view. So we're looking down from the top, the two steel loading plates where we're simulating wheel pairs, and the location of the optical fibers that were used to measure the strains around the circumference of this helically corrugated steel pipe. And then this vertical section showing where the wells were in the pit, which is how we control the water levels. And the idea is that we tested the pipe under these simulated wheel pair loadings before we raised the water level, so when the ground was intact, to get the sort of good soil support response. And then we raised the water level, produced erosion, and then dropped the water level down again to arrest that erosion, to turn it off. And we did that 2 times to look at 2 different levels of erosion. And I'll show you one set of results in a moment. Here are the perforations that Oliver put into the valleys of the corrugations to represent that corrosion. And then he had these steel plates with rubber gaskets that allowed him to block off different parts of the pipe. So we were able to test one half of the pipe where we had perforations on one side only, and we're then able to test the other end of the pipe where we had perforations on both sides. And that top picture shows the optical fibers that we use routinely now to measure strain around the circumference of the pipe. And from the strain, we can infer the thrust and moment distributions. So here's a couple of photographs. Initially, after Oliver had removed the plates at the far end of the sample, so where we had the perforations on both sides. And then after a few minutes of erosion, the surrounding soil has washed into the bottom of the pipe and left a void on the outside. Oliver then filled those voids with foam so that when it was exhumed, we could see the geometry of those erosion voids, and that shows a picture of Oliver down in the pit. The depth from the pipe of the voids varied, but the contact between the void and the pipe was pretty consistent. So it was a sort of little angle of soil, if you like, where or angle of the pipe circumference, I should say, where the soil pipe was lost, and it was reasonably prismatic, so reasonably uniform along the pipe. And so, yeah, so here's some example data. So we tend to do these surface loads a number of times because initially we get quite a bit of plastic deformation in the soil. And then after a few cycles, we tend to get sort of elastic unloading and reloading and unloading. So these are that sort of more elastic behavior on the 4th load cycle under a 50 kilonewton wheel pair. That's about half of the fully factored service load that you'd expect or you'd require in Ontario for one of these structures. And what we're showing in these 2 pictures are the distributions of moment around the circumference as a result of that surface load. The surface load on the ground surface over the crown produces a moment peak at the crown, and 2 moments of opposite sign in the shoulders. So on opposite to that, or adjacent to that point of peak moment. And you can see that where the lines that I've designated with an arrow there and a label as no void, you can see that the moment response is pretty much that response at the crown because of the surface load. But then you can see the half and full void erosion on both sides in here on the left-hand picture and just on one side in the right-hand picture, where after erosion, we get this very large moment developing in that vicinity of where the soil support has been lost. And in fact, that moment becomes the maximum moment and would control the strength of the structure. So it would no longer be controlled by the moment at the crown. It would be controlled by the moment at this erosion void. So it's giving us real understanding of the impact of this type of erosion void, and it's giving us data that we can then use to calibrate finite element models and perform parametric studies. So we saw approximately prismatic geometry where the soil was lost at and at the interface between the soil and the pipe. And we get these large moments at that point. I didn't show you the thrust values, but there were modest changes, but much more substantial moment changes as a result of loss of soil support. The moment magnitude wasn't greatly impacted by the depth of the void away from the pipe. It's mainly controlled by that angular size of that zone where the soil support's been removed. And we saw that the critical moment moves from the crown to that zone of lost soil. And in fact, the impacts under first load cycle were even higher than under that fourth load cycle. I talked a little bit about simulating deep burial with the actuators, with these steel plates. And part of the reason we're able to do that is having moment release joints between the steel grillages and the actuators. So we designed and built these sort of moment release bearings. And what that does is that when we apply force to those vertical plates, those vertical forces to those horizontal plates, let's say we're testing under a flexible pipe, like this steel rib reinforced polyethylene pipe, that pipe is much less stiff vertically than the soil surrounding it. So if we didn't allow the plates to rotate, we'd actually get lower stresses under the center and higher stresses out at the edges. But because we allow the plates to rotate, the moment is released and we get approximately uniform pressure representing that column of soil over the top. And then I'm just going to finish, I think I've got just a few more minutes, talking about another project where we're looking at joint leakage. We've done a number of these tests in the split box, but this is a nice test on a 600 millimeter diameter polyethylene pipe with a gasketed bell and spigot joint. And the joint located near that fault, the location of the fault. And then, of course, we drop the left-hand part of the floor of this pit and subject the pipe to sort of longitudinal bending. And then that's going to impose demands on the joint. And this a bit of a complicated picture here, so let me try and walk you through it. Let's look at the bottom part of the picture to start with. On this vertical axis in the bottom half of the diagram is the fault offset, the amount of fault offset. And on the horizontal scale, we've got the time of the experiment. So we had no movement for the first about 900 seconds. And then we lowered the floor 10 millimeters, kept it constant for another few hundred seconds, and lowered it another 10 millimeters, and so on. And as we were doing that, we're monitoring the vacuum that had been imposed in the polyethylene pipe. So normally a gravity flow pipe like this, we're thinking of the water pressure actually being from the outside. So the sewer is actually below the groundwater table. And our goal with the joints is to stop water coming into the pipe as much as it is to stop wastewater getting out. And so we use vacuum in the experiment to impose that external pressure. Of course, it's air pressure that we're getting rather than water pressure. And then we monitor that vacuum, and that's the top half of this graph is the vacuum pressure with time. During that first phase, as we're pumping the vacuum out or producing that 35 kilopascals of vacuum. And then a steady decrease in that pressure because there's a little bit of loss from our system with time that's got nothing to do with the joint. And then when we got to a vertical displacement of 19.4 millimeters of the floor, we saw a sudden loss of pressure. That's what we've called phase 3 of the experiment. We allowed it to sit for a few hundred seconds, and then we reimposed vacuum pressure. So we pumped again, and we were able to reimpose vacuum, probably because the gasket relaxed and once again sealed the gap between the bell and the spigot. And then we continued the experiment, and we found that at 24.7 millimeters, we had further leakage. And that leakage was so severe that no amount of time was enough to cause the joint to reseal. It was just a permanent leak that developed in the joint. So we can monitor the pipe's deformations using linear potentiometers and using digital image correlation. And we're able to see how much rotation angle actually developed across the joint at these two different levels of floor movement. So at the 19.4 millimeters of floor movement, we had 0.44 degrees of rotation. And at the 24.7, we had 0.58 degrees of rotation. And that's significant because these joints essentially are designed not to leak up to 2 degrees of rotation. And what we're seeing is leakage at much smaller amounts of rotation, simply because we don't just have rotation, we also have shear. So in this slide, here's how we've interpreted the shear force. This was obtained by measuring strains along the pipes and getting moment distributions and then taking gradients of moment to get shear force. And so we're able to infer from the optical fibers what is the shear force when it started to leak at 8.9 kilonewtons of shear, and the shear force when we could no longer get it to seal at that second leaking event, so 11.3 kilonewtons. And so really the reason why we're studying this is because differential settlements occur along pipelines due to various factors, slope instabilities, various construction conditions, but it's also something we're expecting to result from climate change. Climate change is producing loss of permafrost in the north, but it's also changing water levels in the groundwater table position, which will produce settlement, and those settlements will not be uniform. And we've seen here that joints that are designed to resist 2 degrees of rotation without shear in sort of the index tests that ASTM has defined for these structures will actually produce leakage at much smaller values of rotation because of the presence of shear force when it's a buried pipe. And we've seen in other tests on clay sewers, for example, that they're even more sensitive to differential ground movements producing leakage. So I just thought I'd sum up now and talk a little bit about the pros and cons of doing large-scale tests. One of the benefits is that by doing a test in the laboratory on a full-scale system using regular construction equipment, we're doing something that is reasonably realistic, but under very controlled soil density conditions. So we're avoiding the impacts of weather, and also the realities that contractors face with moisture contents in the backfill changing, ground conditions changing, and perhaps a level of site supervision changing during the project and producing unknown outcomes. We can do service loading in the lab, but we can also do ultimate strength testing because we have these high strength actuators and other loading systems to permit us to bring these structures up to their strength limits. And we can test both the soil up to its limits as well as the pipe structure itself. It's efficient to design and execute the test because it's indoors, much easier than to do a big project outdoors. And we have an environment where we can use novel and conventional instruments like linear potentiometers, optical fibers, relatively easily, where sometimes these instruments are harder to use in the field. It allows us to develop design methods or evaluate key design assumptions and approximations that we rely on. And then typically we use computer models to develop design tools. And those computer models and design tools greatly benefit from the authority that we get that comes from a physical experiment. Anything that comes from a computer really is guilty until proven innocent. And we're using the experiments to get that data that says, okay, this seems to be legitimate. So there's some good things. Some of the disadvantages is the facility cost is considerable. So the facilities at Queen's that we're currently using are about $1.8 million worth, I think, of investment on the part of the Canadian and Ontario taxpayer. The incremental test costs of these large experiments are still high, but much lower than field operations. The time is reasonably extensive, 1 to 4 weeks of earthworks. but the students can spend some months preparing the pipe samples with optical fibers and so on. We still need to understand and control the boundary conditions. So, for example, in the deep burial simulator, we have to be mindful of the effects of shear on the side boundaries, and we have lubrication system on the sidewalls to control that shears, but these things need to be figured out and managed. And of course, to do these large experiments with a high level of confidence, we need high quality technical support. That can be expensive. So thanks for your attention. I'd be very happy to take questions. Here's a little slide just acknowledging the people I've worked with. So it's just some of the many wonderful graduate students that have helped me develop and use this facility, some colleagues, and some of the sponsors. Thank you.
Thank you, Ian, for the very informative presentation. For the audience, like, you can use the QA part to post your questions. I'll start with the first question, Ian. It was mentioned that clay sewers are more sensitive than HDPE to leakage during soil movement. What do you mean by clay sewers? I don't think I've heard of that material used before in my area.
Okay, yeah, interesting. So the history of Canada is, of course, different in Alberta than it is in Ontario, because of a lot of your infrastructure was put in after the infrastructure in Ontario. So we have a lot of legacy pipe systems like cast iron water pipes, and sewer pipes traditionally were vitrified clay pipes. So they weren't concrete, they weren't polymer pipes, they're actually vitrified clay. It's a great material. It lasts a long time. So you can go to places like in Turkey, for example, ancient Greco-Roman sites in Turkey, where you can see clay pipes that are still beautiful today after 2,000 years. So they're very durable material, because vitrified clays, it's just glass, essentially. So it's materially durable, but it's quite brittle. And the experiments that we've done at relatively shallow cover in our facility, they can basically, the joints can start leaking at just over 1 centimetre of differential settlement. If it was a deeper cover, which most sewers are, it would be even less settlement, because there'd be even higher shear forces. And so those pipes actually are very much subject to leakage under differential settlement. And a lot of the pipe repairs that we do, say in Toronto, for example, or here in Kingston, where we put in CUIIC in place liners, it's because of leakage that's produced loss of soil support beside those clay sewers, and then fracture of the clay sewers into sort of, you get fractures along the crown and the invert and the spring lines. And it's all because of joint leakage. So a long answer to your short question, mate.
Good. The next question, Ian is asking, have you used any finite element method to compare the results? I know you use finite element, but just for comparison purposes, it seems.
Oh, absolutely. So actually, I started my career as an analyst using finite element analysis and developing closed form solutions, and I'm still doing that to this day. And almost all of the experiments that I've shown you today have been modeled on the computer. Sometimes we're able to develop closed form solutions, so just a mathematical equation, which has some advantages. But generally, the complexity of these problems we're studying means that we need to be modeling them with finite element analysis. And a lot of the design methods that I've developed and have had implemented over the years result from those finite element calculations. So we'll do a parametric study on the computer at much lower cost than we could do by doing 50, 100, 200 experiments in the lab. It's not possible financially, and I suppose time-wise. But to do that on the computer is relatively straightforward. So there's three-dimensional finite element analyses. We've modeled erosion. We've modeled all sorts of repair systems, various liners. We've modeled deterioration, the impacts of deterioration on the computer. Yeah, I could go on, but yes, it's a huge part of our toolkit, and it's that complementary work on the computer that really, which extends the impact of these experiments, sort of extends the influence. And I would say it's the experiments that extend the influence of the analysis, because they give us confidence that the analysis is doing a decent job. And of course, we can see the limitations, and we don't nail it. There's always approximations. There's always limitations in what we can do. Thanks. It's a good question.
Perfect. Next one, Ian, is most of the time contractor cannot install pipeline in sand layer. What is the reason of using sand, not clay or silt in your full-scale lab setup?
Okay, so that's a really interesting question. So a lot of the work that I do is on culverts, and when we bury culverts like a corrugated steel culvert, we don't bury them in clay or silt. We use coarse-grained backfills, because the modulus, or if you like, stiffness of the backfill is a very important part of the load carrying system. So that's for the work on culverts, like the leaking corrugated steel pipe. We would not bury those in clay. We would always use a coarse grained material. Of course, if you're directional drilling, you drill through whatever is there. And often that is fine-grained sediments. A lot of the historical pipes, like cast iron clay, they were backfilled with native soils. So just the silt or the clay or the sand, whatever they took out of the trench is what they put back in. The other part of my answer is it's very difficult to do large-scale experiments in clay. Preparing the clay so that it's like a natural undisturbed clay. For example, if I wanted to do a sort of directional drilling experiment in the lab, it's very difficult to prepare large blocks of clay. Relatively straightforward to put down sand or sandy gravel. And so there is also that practical aspect to it. For the erosion experiment, we used the sand that we did because it's a relatively erodible material and will allow us to do experiments in the space of 1 or 2 hours to do a process of erosion. Whereas if we had a very like a well-graded sandy gravel, it might take weeks for the erosion to develop. So there's some practical choices we make so that the experiments can be done in the time span that we have available to us. And of course, that's all part of managing costs. So hopefully that's a decent answer for you. Perfect.
So the next one, Ian, is asking about, other than cost and ease of installation, why is culvert still used in place of concrete or PVC HDPE when considering the asset life cycle of each of pipe type? Especially after watching your presentation, it's curious why CMP is still spec'd and used as much as it is.
Yeah, so that's a really interesting question. Corrugated steel is very cost effective in the short term, but as you're implying, if you look at the life cycle, it may not be as attractive. I think that there are still lots of circumstances where you can bury a corrugated steel pipe and it will last a long time. And there are circumstances, it's horses for courses. So sometimes you have an environment where the corrugated steel is going to work. Let's say, for example, in a situation where the pipe isn't sitting permanently in a like a permanent creek, it's just something where you have water flow during a storm event, then the corrugated steel is probably going to last 100 years because it's not subjected to that groundwater permanently. It just comes whenever there's a storm event. But in Eastern Ontario, where I live, a lot of these structures, the rivers, the creeks, there's permanent water, and the water's slightly acidic because of the peat and the other organic materials, and maybe because of the rocks in the shield. And as a result, they corrode and they might last, 2 or 3 decades. And so I agree that there's going to be circumstances where it might be better to use a concrete culvert or a polyethylene or PVC culvert, or perhaps a corrugated steel culvert that's been coated with polymer, which you can buy the polyethylene coated structures now. So there's a bunch of choices, and I think we need to make the right choice for the right location. Yeah, so sometimes corrugated steel is going to be the best option, and sometimes it's not. Yep.
Perfect. So the next one is not a question. Perhaps I'll wrap up with that one. A comment from Bill Garibaldi saying, just a thank you for a great presentation. It is so interesting to hear the research you are doing, and a big thank you for your simplified explanation. So
thanks, Bill.
Thank you, Ian, for accepting our invitation and giving the talk. And thank you all for attending the CUIIC webinar. Looking forward to seeing you all in 2023 for the rest of webinars from CUIIC. And I believe that concludes our session today.
Have a great holiday, everybody.
Thank you.